This is the solution to test number 2, version C for EE206, circuits 1. The first problem is find the Thevenin equivalent of the following circuit. Here, one way to do it is source transformations. Here, this is already a Norton equivalent. Let's convert this to a Norton equivalent and that to a Norton equivalent. When I do that, I'll wind up with 3 current sources in parallel. Essentially, this becomes your current, voltage, and resistance, plus 3 resistors in parallel. So doing that, the 50 volts, 50 ohms becomes 1 amp, V over R, and 50 ohms. This becomes 3 amps and 25 ohms. The current then is 3 amps plus 1 amp plus 2 amps, 6 amps. The resistance is 100, and parallel with 50 and parallel with 25 gives you 14.26 ohms. Converting back to Thevenin, the Thevenin voltage is I times R. 6 amps times 14 ohms gives you 85 volts. So there's your Thevenin equivalent. That's one way to do it. Problem 2 says try to find the Thevenin equivalent for this circuit. This one's a little bit trickier. The Thevenin voltage is the open circuit voltage. Call this X. X is whatever it takes for the currents to balance. So that'll be minus 2 plus X over 100. This will be 10X plus X minus 10X over 50 plus this current, X minus 75 over 25 equals 0. Solve for X, I get minus 38 volts. Now to find the resistance, turn off the sources, so this becomes 0 volts, 25 ohms to ground. This is 0 amps, basically knock it out. Apply 1 amp or 1 volt test source, makes Vx equal to 1, makes this 10. Then the current drawn will be 1 over 25 plus 1 over 100 plus 1 minus 10 over 50. So the current then is minus 130 milliamps. The resistance is V over R, becomes minus 7.6 ohms. So this is a strange circuit. This actually has negative resistance. The third one is find the Thevenin equivalent given this data. The simplest is to say that the Thevenin voltage is the open circuit voltage. That's right here, 28.5 volts. The Thevenin resistance is V over I. If I take 28 volts and short it, I get 73 milliamps. So the resistance must be 390 ohms. Given these two, I can find max power transfer. Max power is when our load equals our Thevenin. At that point, the voltage across the load is half the source, 14.25 volts. The power then is V squared over R, 520 milliwatts. Problem 4 tries to find the voltages for an op-amp circuit. An op-amp circuit with negative feedback, here the trick is that V plus equals V minus. So if this is 10 volts, V1 is 10 volts. By voltage division, V5 is 8 volts, so V3 is 8 volts. Now, if I have 10 volts across 1K, make that 10 volts across 1K is 10 milliamps. This is also 10 milliamps. 10 milliamps at times 2K is 20 volts, so 10 volts plus 20 volts is 30 volts. 30 volts going to 8 volts gives you 22 milliamps. That 22 milliamps has to flow through here, so that's 66 volts. 8 minus 66 is minus 58 volts. That's problem 4. Problem 5 is write the node equations. Here, to start with the output, the first equation is V3 equals V4. Then at V1, current up, down, and right add to 0. Node 2, up, down, right add to 0. Node 3, left, right add to 0. V4, left, right add to 0. Node 5, I can't write the node equations because I don't know the current from the op-amps, plus I already wrote it. The node equation V5 is V3 equals V4. V plus equals V minus. So these should be your 5 equations, 5 unknowns. And the last problem, if I want to design a circuit that goes from plus 10 volts to minus 10 volts as resistor goes from 650 to 750 ohms, the trick is pick a voltage divider. Here I pick 700 ohms. That's somewhat arbitrary. If you do pick 700 ohms, this voltage goes from 4.8 volts at 650 ohms to 5.17 volts at 750. As the voltage goes up, the output goes down, so connect to the minus input. The gain is the output of our input. Output changes by 20 volts as the input changes by 0.3, so I need a gain of 55.9. And the offset, I want the output to be 0 at mid-band. The midband is the average of the two, 4.994 volts. So there's your circuit. That's the solution to test number 2, version C.